So a correlation function is actually a relatively straightforward thing. There is a 2-point correlation function, which is saying if I have 2 points of the universe, let's say this point and this point, and I know, say, the density at this point or the temperature at this point, the 2-point correlation function tells me some probability distribution about the density or temperature at this point. In full generality, the 2-point correlation function would depend on the actual location of both of the points. So it would matter whether I'm up here or over here, or whether the other point is here or over here. But in a universe that is on average, again, this word homogeneous, so on average, it's the same everywhere. And now a new technical word, isotropic. So it looks the same in every direction. These are two subtly different things. I'll explain why. You could have something that is moving in this direction. The whole universe is moving in this direction. Like every piece of material is moving that way. So the stuff here is moving that way, 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 and stuff here is moving that way. This is still a homogeneous universe, but it's very far from isotropic. If you're anywhere in the universe and you look this way, you see stuff moving away from you. And if you look this way, you see stuff moving towards you. So it's not isotropic at all, but it is homogeneous. On the other hand, you could be sitting at the center of a universe where in every direction you see exactly the same thing, but it could be some spherically increasing density. Every new sphere is somehow increasing in density. So it's still isotropic. Every direction you look, it's the same. It's only isotropic for you. It's not isotropic for anyone else, but it's not homogeneous. But okay, if you have a universe that is both homogeneous and isotropic, looks the same everywhere, sorry, is the same, well, is on average the same everywhere and looks the same in every direction, then this 2-point correlation function only depends on the distances between things, which is kind of straightforward to see. Like if the universe is the same everywhere, it doesn't matter where my reference point is because it's the same everywhere statistically. And then if it's isotropic, it doesn't matter whether the point I'm now trying to predict is over here or here or here or here or here or here. The angle doesn't matter. But of course, if I'm further away, it might be different to if I'm closer. So the 2-point correlation function then becomes a function just of the distance between the 2 points. And you can maybe start to see how knowing about inflation becomes something that helps you to know about this correlation function. Because as I was saying before, in inflation, as the accelerated expansion is causing stuff to get further apart and eventually not be able to interact, stuff gets frozen in. So then later on in time, when this, after a decelerated period, when the stuff that's far apart starts to come back into causal contact, it starts to be able to interact with each other again. You start to be able to look in one direction and in the other direction and see these two pieces. That whatever was frozen during inflation has now become a measurable thing. Now, I've just talked about the 2-point correlation function. There's also 3-point, 4-point, 5-point, 6-point, 7-point, 8-point, 9-point, 10-point correlation functions, n-point correlation functions where n can take any value. A 3-point correlation function is exactly what it sounds like. You have this point, you have this point, and then I only have 2 hands, but if I had a third hand, I'd put my third hand here and say a third point. So in that sense, it then becomes a function of triangles, right? You got the 3 points. So 2-point correlation is just a distance. A 3-point correlation function is a triangle. And the homogeneity and isotropy comes in here in the sense that the triangle doesn't have to be anywhere at a specific point in space. You don't say, oh, the triangle that's over here is different to the triangle that's over here. All triangles are equally, wherever they are in space, equally relevant. And then isotropy means the kind of orientation of the angle stops, of the triangle stops mattering. You just, a 3-point correlation function just depends on the shape of the triangle. So an equilateral triangle might have a different 3-point correlation function to an isosceles triangle, but an equilateral triangle that is like this is going to be equivalent to one that's like this, or like this, or like this, or like this, or in a different point in space. And just like with the 2-point correlation function, distances matter, so the size of the triangle is also relevant. And equally, this applies to 4-point correlation functions. You just have a, not a rectangle, but a parallelogram. I think it might be quadrilateral, 4-sided figure. Again, where it is in space and what its relative orientation is, doesn't matter.